Hello guys, in this video I want to take you through a very important design engineering framework which is called as the quality function deployment, or otherwise called as house of quality, which is a very common framework, common tool used in major OEMs in the design of products. So let's say if you're developing a very simple mechanical tool, let's say for example a spanner, a very simple spanner. Now what are the user needs? The user who is operating the spanner to perform a function, which is to tighten a bolt, has specific needs. What are those needs? First need is that the spanner should fit into the appropriate bolt head. So if it's written 17, then it should fit into the bolt head which is having a cross flats as 17. It should be ergonomic to rotate, it should be ergonomic to operate, it should be easy to hold, it should be rigid and durable. So when we are applying the torque, it should not break, it should not bend, and also it should be slim and not too bulky to operate. These are very simple user needs for a simple mechanical tool like a spanner. Now these are user needs which are coming from the user, from the customer. Now the engineer, the design engineer who is designing the tool will have certain engineering specifications which will drive the design. So these engineering parameters which are driving the design will be design geometry. What is the geometry of the spanner? What is the profile of the spanner as a whole? What is the material of the spanner? So for example, over here it's mentioned chrome vanadium steel. So what is the material the design engineer is selecting for the spanner? So next is what is the design profile of the handle? How is the design of the handle? How is it shaped? Whether it's ergonomic or not to hold for the user, and also the dimensioning and tolerancing of the across flats over here. So that depends on the fit which will take place between the bolt head and the spanner. So the dimensioning and tolerancing also is another important engineering parameter which will be governed by the design engineer in the design of the tool. So you can see that there are user needs and then there are engineering parameters. Now it is clear that the design engineer who is responsible for designing the tool should satisfy the user needs by setting the appropriate engineering parameters. So the design geometry, the material, the handle design profile, the dimensioning and tolerancing should be appropriate to make sure that the user needs are being met. So this is the crux of design engineering. Design engineering is designing to meet certain user needs or certain engineering requirements by setting the design parameters of the product or the system, which is done by the design engineer. So some key questions which come up is that while designing to meet the needs with the high quality output, it requires knowing how important is each need relatively, how is each need related to the engineering parameters. So establishing relationships between engineering parameters and the user needs is a very critical stage for design engineers to design a product which is satisfying user needs by setting the engineering parameters. So you need to know the relation between them, between the needs and the engineering parameters. And also we also need to know the interrelationships between the engineering parameters themselves. And finally, if we are developing multiple concepts for the same design, we need to know how to compare the multiple concepts based on various user needs and various engineering parameters. So this will lead to a design which is high quality, and we would have come up with a thoughtful design where we are considering each and every need, we are prioritizing the need, we are relating the need to the engineering parameters, and also establishing interrelationships between various engineering parameters and the output. So it is clear that for successful and high quality product design, we need to have a clear understanding between the relationships of the user needs, that is the needs of the customer, and the engineering parameters of the system, how they are related, which is more important, which is less important, how is there an interrelationship between them. So understanding that is very important. Hence for that, a framework has been created which is called as the house of quality framework, which is otherwise called as quality function deployment. So it is basically listing down the customer requirements or needs, which is called as the voice of customer. So this is basically a list of customer needs. Next step is to set the relative importance of each need. So each customer need, generally written in the form of statements, which is a voice of customer, is not equally important. Some are basic needs, which are non-negotiable. Of course, they cannot be, they have to be met. There are certain performance needs which, when the needs are being met, they lead to high performance. And then there are needs which are delight needs, which are needs over and above the basic and performance needs, and which lead to delight of the customer, which when they are not met will not affect the performance, but when they are met it will lead to customer delight. So there are different types of needs. For example, in a car, having tires and having locomotion or moving from one place to another is a very basic need that is non-negotiable. And having a car which can accelerate well is a performance need. But having a car which is having, let's say for example, a sunroof, right now it might be a performance or a basic need, but in the earlier days of the car, having a sunroof was a customer delight or source of customer delight. The customer did not ask for it, but it led to a lot of happiness for the customer because it was a great feature. So those kind of needs which are not related to performance or not related to basic but can lead to delight. So there are various levels of needs. So those needs or customer requirements have to be categorized based on that relatively. Next, we tabulate the engineering parameters or technical attributes or characteristics of the design which can be modified by design. So those are tabulated in various columns. So these are all rows, 1, 2, 3, 4, like that. They'll be rows, and then each will have the relative importance, and then there will be columns, 1, 2, 3, 4, 5, 6, like that. There will be columns of engineering parameters. And then there will be a relationship matrix between the customer needs and the engineering parameters. The relationship matrix will be which need is directly being impacted by which parameters. So that is being captured in this relationship matrix. Then there is an interrelationship matrix between the engineering parameters, which engineering parameters is dependent on other engineering parameters. Changing one engineering parameter will affect the other positive or negative way. So there are many engineering parameters like that in designs. Next, we do an importance weightage. So based on the relationship and the criticality of the customer requirements or customer needs, importance weightage is given, and the various engineering parameters are basically ranked based on their importance by the value of the relationship between the customer needs and the engineering parameters, and the ones which are important are rated highly. The next set of entries would be the measurement units of each parameter. So each engineering parameter can be objective or subjective. For example, an engineering parameter would be torque. Engineering parameter would be yield strength of a material. So any of that will have an objective measurement unit that will be listed over here. Then finally, on the right hand side, we have rows in which the ratings of the current design in meeting each requirements is basically put down. So the current state of design is rated in terms of the various customer requirements or customer needs, whether it meets those requirements or not. And then the next list of rows will have the ratings of a competing or a new design in meeting each requirement. So basically you can compare two designs over here, whether which design will meet the requirements more closely as compared to the other. Here is a QFD example in an Excel sheet of an adjustable spanner. So here is the list of user needs: comfortable grip, easy to adjust, durable, lightweight, affordable, high torque capacity, range of fasteners which can be tightened. This is the weightage or rating based on the importance of need to the user. Some needs are more important as compared to others. Higher value means more important, lesser value means less important. Then these are the engineering parameters: handle design, length, width, section, material strength, material hardness, and adjustment mechanism precision, max torque which can be applied, range of adjustment. And this matrix in orange is showing the relationship between the needs and the engineering parameters. Higher the value, more the relation is there between the need and the engineering parameter. 9 means highest, 3 means medium, 1 means low, and 0 means no relationship. And this matrix on top is the interrelationship between the engineering parameters. So material strength will have a direct relationship with the material hardness. It can be positive, it can be negative. Adjustment mechanism precision will have a direct relationship with the handle design. Max torque which can be applied will have a direct relationship with the handle design. Of course, the handle design, the section will have a direct implication on the max torque which can be applied. The adjustment mechanisms precision will have a direct implication on the range of adjustment of the spanner. Like that, this is the matrix for the interrelationship between the engineering parameters. So this section is what versus how, relationship between needs and parameters. 9 is strong, 3 is medium, 1 is weak. And this is how the user needs will be met, that is the technical parameters and characteristics. And this is how versus how, that is interrelationship between parameters. And then the weighted importance of each of the engineering parameters. So we find out the weighted sum of these 9 into 5 plus 4 into 1 plus 5 into 9 plus 3 into 9 plus 4 into 9 plus 4 into 9 plus 3 into 1 will give 196. So weighted importance, and that will give us a rating of the engineering parameter and tell us which engineering parameter is the most critical. And the bottommost one is the measurement units. So handle design, material strength is measured in megapascal, material hardness in HRA. So I've tried to explain in a very simple way the QFD framework with a very simple example. Of course, this QFD framework can become very exhaustive with large systems. For example, let's say if you take a suspension system of a car or the car as a whole, then this QFD framework can become very, very exhaustive. But for designing smaller products, simpler products, for design engineers, this can become very easy tool to use to basically find out the relationship between the customer requirements and the customer needs and the engineering parameters, and establish which engineering parameters is the most critical to meet the customer needs. So why do design engineers need to use QFD framework in the design process? First, it prioritizes customer needs and requirements. So you learn how to prioritize certain customer needs and requirements over others, which are the most important. The next one is, if you prepare a QFD, the House of Quality framework, for the product which you are designing or the system which you are designing, you know changing which engineering specification affects which requirement or need. So you have a direct relationship matrix which allows you to track which engineering specification will have an impact on which type of requirement, which type of need, if the QFD has been made thoroughly. Next, you also know the criticality of the engineering specifications. So certain engineering specifications are very critical, and hence the criticality of the engineering specification will allow you to justify the additional tighter tolerances which can be put into the drawing for those critical specifications. So this also gives you certain critical parameters which need to be controlled much more accurately in the manufacturing process. So criticality of engineering specifications is what you will get from this. And finally, you will improve the quality of the design. Overall quality of the design will be improved because this is a very holistic way of capturing various needs and establishing relationship between the various needs with the engineering parameters, and then also comparing those and finding out the important engineering parameters, important customer needs. So it improves the quality of the design overall.